Hello, welcome to the third introductory video lecture in this compilers course. My name is Anoop, and we're going to cover compiler, like some more details about the compiler and some close cousins of the compiler. Things that are not exactly compiler but share a lot of the same DNA. So when we looked at what a compiler does in the previous introductory slide, we kind of cheated a little bit. We said that the compiler directly produces an executable binary when it's given in an input source program, but that's not really the case. It actually, every compiler produces assembly language output, which then passes through an assembler, and then that produces an executable binary, which then goes into the runtime, and the operating system loads it, runs it, and you can provide it some input, and you get the output. A close cousin of the compiler is something called an interpreter. As you can see, the interpreter looks a lot simpler than the compiler. Where the compiler creates, for the entire input source program, it creates the assembly language equivalent of that input source program. The interpreter instead reads the source program and then executes it line by line. And so the interpreter itself is required in order to take some input into the program and produce some output. The interpreter itself comes as part of the runtime, right? So the entire source code analysis part, the code generation part, all of that is built into the interpreter, and then the interpreter is needed at runtime when you're running your program. So the main difference between a compiler and an interpreter is that a compiler is static. It can statically analyze the input programs sort of as a holistic one-step process, looking at every possible part of the input source program. And as a result, it can probably find things that are wrong with the input program. It doesn't have to wait until it reaches the runtime in order to find bugs. Whereas an interpreter is dynamic because it's executing these instructions. Sometimes it can only find errors in your code at runtime, like when you're running, even though there might be problems in the source code that you could have figured out by doing a static analysis. Another cousin of the compiler is a compiler that, instead of generating assembly language, generates what's called bytecode. Bytecode is very similar to assembly language, but it's not for a machine that actually exists. So it's a highly abstracted form of device called a virtual machine. And the main advantage of this is that a virtual machine doesn't have the same constraints. Like, it doesn't need to have a fixed number of registers, for example. It can have infinitely many registers. A virtual machine itself doesn't have the constraints of hardware. It's a completely software defined machine. So it can be useful, for example, in generating a sort of machine language that is much more abstracted away from the hardware. And this can have some benefits. For example, if you look at Java, the Java compiler produces bytecode which is run on the Java virtual machine. And one of the advantages of this is as it's running the code on this virtual machine, it can do optimizations on the fly as it's running the code. It's called just-in-time optimization. So the difference between compiler that produces assembly language and a compiler that produces bytecode is that this one is a mixture of static and dynamic. So if you look at this part over here, this part is static, just like this part of the compiler over here. But however, this aspect of running it on a virtual machine is more dynamic, because it can dynamically adapt to the situation, and it's can catch errors in the source code at this stage over here in the static phase, and at the same time have the benefit of an interpreter in that it can dynamically execute the bytecode and take advantage of this dynamic execution. So compilers can be split up into two main parts. So the front end, which is analyzing the source code and producing a kind of representation that is then exploited to synthesize the code or do the code generation. And that part is called the back end. So the front end is responsible for all the source code analysis, and the back end is responsible for the code generation and optimization. So you can think of it as a translation task. So it's a translation task from a source code to an executable. And I want you to think about, how is this different from other translation tasks? Is it similar or different from translating from one language to another? Like, for example, if I was to translate from French to English, is that process of translation any different from translating a source code to an executable? Are there similarities? Of course, there are differences. I want you to think about that. Requirements for a compiler are quite simple. You need to support high-level programming languages. So your compiler should not say, oh, it's too difficult for me to handle functions. It should have the ability to deal with the high-level programming constructs that we're used to. It should have good error messages. It's quite frustrating doing programming, and a good compiler should tell you where the errors in your program lie, and so that you can fix them. The speed of compilation is an important aspect of a good compiler. You don't want to wait around for a long time to wait for your program to compile. So a good compiler should compile the code very, very quickly so that the programmer is not waiting around. And finally, your compiler should produce fast executables. So when it produces the executable at the end of this process, it should run quickly, and ideally should have a small footprint. It should not be a very huge binary file. The smaller the better. So these are just the desired requirements of a compiler. And different compilers achieve this to some degree. Some are better than others in some of these aspects. So the compiler doesn't sort of exist in a vacuum. It exists as part of a tool chain. And so when you have, so essentially when you're generating output from a compiler, you're generating assembly source. So you take all of these assembly source files, you run it through an assembler. So that's this phase over here. And what you get as the output is an object file. So for each assembly source, you get an object file. All of these object files are linked together using a linker, and you can create a library out of these functions. So this is often how you build more complex systems, is you take a commonly used some kind of computational problem that needs to be solved by and used by lots of people. You write source code for it, you compile it, you get assembly, you create an object file, and then the linker is crucial in converting all of those useful functions you've written into a library. And then finally, that can be linked together with your code that uses that library and create an executable. So I've created a small demo to help you understand the job of the linker, and that's what I'll do next. Explains how linking works. I expect you've seen this before if you've written any reasonable size programs, but just to make sure everybody's on the same page, I want to just go through a simple example of linking and dynamic linking in Linux. The source code for this, so you can download it and follow along, is available on the compiler's course website. The link to the website is available on the discussion board, or you can go to my homepage and follow the link to the compiler's course website. What you're looking for is in the syllabus section of the website, in week 1, Introduction to Compilers, you're looking for the link on dynamic linking, and download the zip file that is linked over here. So when you download it, it will download a file called dilib.zip. Downloaded the file dilib.zip from the compiler's course website. The next step is to take this file and copy it over to a Cecil Linux machine. I'm going to take this file dilib.zip and copy it over to a machine that is in the Cecil Labs, and this colon will tell me where to put it. I'm just going to put it in my home directory, and this copies the file over to this Cecil Linux machine. The next step is to SSH to that machine. The instructions for all of these are on the Cecil website. And what I then want to do is look for my dilib.zip file, which sure enough has been copied over. I'm going to make a directory to keep these files and change my directory into this new directory that I made. And then I'm going to unzip the dilib.zip file into this directory. As you can see, it has expanded out these files. So dlhello.c, english.c, hello.c, korean.c, and makefile. Makefile is something we'll use to build our programs. It contains the recipes to call the compiler to build the program. So what are in these files? So let's take a look at them one at a time. So cat is a program that prints out what's in a file. So if I look at what's inside hello.c, it's a very simple program. It has a main function, which is where the execution would start, and it calls a function called greet, but it doesn't define this function. It just has a definition of what the function should look like. It returns nothing, so it returns void, and it takes no arguments. This is a tutorial about linking. I'm going to try and create a library that contains a greet function and link it with hello.c in order to provide this greet function to hello.c. So I have a file called english.c which contains a function called greet, and all the function greet does is print hello world. So it's a very simple function. There's also another file called korean.c which also has a greet function, but it says hello world in Korean. So the question is, how can I make sure that I get this greet function link up with the right one? So if I wanted to say hello world in English, it should link with this function, greet in English.c. If I wanted it to print hello world in Korean, I would want it to link with this function, greet in Korean.c. So let's see how we can do that. The makefile contains instructions for how to make various executables in this directory. So I know that it contains a recipe for making a statically linked binary. So it's going through a various number of steps here. So the first step is it's compiling English.c into a object file. The PIC here stands for position independent code, which is needed if I wanted to take this object file that it's creating from English.c, which is English.o, and I want to create a new library. This library, which is called libenglish.so, contains this greet function in English. And I'm defining it as a library that can be linked with other programs. In exactly the same way, I'm creating a Korean.o object file, and then using this command, cc-shared, I'm generating a Korean version of the library, which contains a greet function, which says hello world in Korean. Now I'm going to create an object file. So -c here just creates an object file from a C program. I create hello.o, so that's hello.o, and it creates a binary English hello by looking at the current directory, because I created the library in the current directory. The -L command option is to look for the libraries in a certain directory. So dot in Unix is the current directory. And -l tells me the name of the library. And by convention, the name of the library, you always append lib before it and .so after it. So it's going to look for libenglish.so. And in this command over here, it's going to look for libkorean.so. If I run English hello, it's going to say hello world. If I run Korean hello, it's going to say Sesang Annyeong, hello world in Korean. An example of static linking, because if I look at the file hello.c, I can only have one greet function linked to this program at a given time. So I had to create two different binaries, one for the English hello world and one for the Korean hello world. What if we could do this dynamically? So at runtime decide which language we want to use, which greet function I want to use, so that I can print. If I provide the English version of the library, I should get the English hello world. If I provide the Korean version of the library, I should get the Korean hello world. Is it possible to do that? Right? Turns out you can do that by using a dynamically linked library. So if I look at a file which is also provided to you called dlhello.c, this looks a little bit more complicated than the simple hello.c that we saw before. So what is it doing here? Well, the main things to look for are these functions, dlopen, dlsim, and dlclose. Those are the functions that manipulate dynamic libraries in Linux. And it takes an argument. So this program takes an argument, and it says, I'm going to open that argument as if it's a dynamic library and link it dynamically, so that when I run this program, it's going to look for a function. So this string contains a function name that it's looking for inside the library. So as long as this library has the function called greet, it will run it. And the way that it runs it is by getting a pointer. So here, this line over here gets a pointer to a function, and this line first checks if that pointer is not null, and then calls, so dereferences the pointer to the function and calls it with no arguments, because greet is a function that takes no arguments. And then when it's done, it closes the dynamic library. So let's look at how this particular more complicated but somewhat more useful version of a dynamically linked hello world. Link dl hello.c is quite simple. I first just create the object file. So this creates dl hello.o, and the next step is to create the binary, which I'll call dl hello, which takes the object file, and I need to tell it that it's going to use a dynamic linking library. It's not a library that's linked by default. So in order to find the references to DL open and the other dynamic library functions, it needs to actually load this library, which is called DL for short, but somewhere on the system there is libdl.so. And now when I run dl hello, it expects an argument. If I give it the same library that I built, which contains the English greet function, it prints hello world in English. And if I give it the Korean library, again the same library that I built before that I statically linked to get the Korean hello world, now it dynamically uses the greet function from this library at runtime and uses the Korean version of the greet command to print hello world in Korean. So we talked about bootstrapping before at great length in the Trusting Tust video, IN2. Let's look at it from a more practical perspective when you're writing a compiler. So often you want to write a compiler for a high-level programming language, and you want to write the compiler in the same language. You know, sometimes you can write it in an existing language like C, and that's fine. But sometimes you don't have a choice, and you're in a situation where you really don't have any compilers on that system, and you need to write a compiler for a programming language that can be used to program that system. So you have to start from nothing and get to a point where you have a usable programming language. And that's a problem that we addressed using the technique of bootstrapping. So the idea is you start with a very simple subset of the language first. So let's say that you start with expressions, and maybe you have a goto statement, and that's all you have. Now you take this very, very simple programming language, and you write your compiler, and this compiler is written in assembly language, and you get your first compiler that understands expressions and goto statements. So let's call that compiler sort of 1 for the first stage. And now what I can do is I can use compiler 1. It does understand expressions and goto statements, and use it to implement expressions plus goto plus some new aspect that's going to be useful in the language. Let's say functions. So it implements functions, and now it goes through compiler 1. You get a new compiler. Now this compiler can understand how to deal with functions in this programming language. So you can see the pattern here. I can now use this as my new compiler, and I can add some new features to the programming language. So maybe I can add for loops and while loops, and that's going to be useful. It makes the language more powerful. And now I have a new compiler compiler 3. And if I keep doing this, in the end, I get at the end stage, I'll have a compiler star, which is my ultimate compiler that can accept any program in my fully fledged programming language. Another way to bootstrap an implementation for a programming language is to just write an interpreter for it. So you write the interpreter in a lower level language. For example, the Python interpreter is written in the C programming language and allows you to write Python programs, but it depends on the C compiler in order to do this. The other idea is if you actually want to generate ARM executables, which ARM is a different kind of CPU architecture, different from x86. What you can have is a compiler that's running on an x86 machine, but produce ARM code. So you can run the program, or you can run your compiler now on an ARM machine, where the original compiler ran on x86. So this kind of cross-compilation is another attractive way to bootstrap from one architecture to the other. So what are some modern challenges in compilers that people are working on at the moment? There's instruction parallelism, which is trying to execute as many instructions as possible at the same time by taking advantage of the hardware that exists now. There's quite a lot of ways to exploit the workings of the CPU to make sure that there is no idle time, and all of the time that it has available to it is spent executing instructions. So this is we're actually going to study some of this during the optimization part of the course. There's a lot of challenges in writing compilers for programming languages that support parallel algorithms. So there's new programming languages that need compilers that are aware of grid computing. So you have many machines all networked together and you want to use them all effectively. Or multi-core computers, so a chip that contains 60 or 120 cores. We need some help. Programmers need help from high-level programming languages, and therefore they need good compilers in order to be able to generate good code for these kinds of environments. Finally, we want to exploit the memory hierarchy. As you know, the fastest thing you can do is to have your data in a register. The next fastest to put it in a cache, like a L1 cache or L2 cache. And the next fastest is to put it in RAM. And a compiler that's sensitive to all of these characteristics of speed of memory can produce much faster code than a compiler that is unaware of these constraints. There's a lot of work on compiler methods that can help make it easy to program devices such as GPUs, quantum computers, DNA computers. So GPUs are fairly widespread. There's not that many quantum computers out there, but there are a few. And DNA computers are still sort of at the fringe, but who knows? They might be usable for general computation in the next couple of decades. So compilers in these kind of devices are an interesting issue and requires a lot of work. Finally, there's an extreme form of inner loop optimization. So as we know, when we are using a CPU, we rely on CPU instructions that are pretty low level, like you're adding two numbers, subtracting two numbers. What if you could take a program, analyze it using a compiler, and then create new instructions and hardware that are specific to those functions. So for example, if you had a function like that does matrix multiplication, what if you could generate hardware based on the analysis of that function that does matrix multiplication? It's an extreme form of sort of optimization where you're actually creating a hardware representation of a particular function in a high level programming language. So this can be done by using FPGAs and technology like that. And this is kind of one of the cutting edge of compilers nowadays.